Hello everyone. Today we will start from our address decoding section. In this section, we will discuss about programmable decoders. First of all, we have PLD, which is programmable logic device. It have three types: PLA, PAL, and GAL. PAL is for programmable logic devices. Then PAL is for programmable array logic and gated array logic. In programmable array logic, we can easily program the logics, and the programmable array logic where we cannot easily conduct. In PAL has replaced PROM address decoder in a latest memory interface, typically constructed with AND, OR, and NOT logic, which is used in PAL. PALs are programmed using software such as PALASM, and then many examples in text use PAL decoders. In class, we will use the logical gates directly, but in practically PALs can be reduce the chip count. So this is a simple PLD, which is programmable logic device. Now we are in the address decoding section, and here are some basic maths. You can have a snap of this one. This is used in 74LS138 from 3 to 8 decoders. Now moving to the next. Here we have again a math where we need to design a 64K into 8 selection of memory for 8088 using 8K into 8 2764 EPROMs. The memory starts address is A0000. The steps: architectural questions. How many chips are required here? We have 8 chips which are required here. Now, how many address lines go with the 8 chips? Here we have 2764, which can be generated by 2 to the power 3, which generated 8, and then 2 to the power 10, which generated the value of 2k. So we have 2 to the power 13 locations. So we need only 30 address lines to generate this one. And now only 8-bit data bus with one bank. Deterministic questions are: we need a 64k. The 64k can be generated by 2 to the power 6 into 2 to the power 10. So we have total 2 to the power 16 byte of memory blocks, and the start position is A000 and the size is 1000. The lower size is the starting form and the higher size is the lower form plus the size then minus 1, which is AFFFF. Now for the beginning position we need to generate A, which can be generated by this section, which is A, and all other implements are 0. Now we need to generate A, which denotes that one, then F, 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 and again F, which will generate A, F, 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 F. Here we have const, which enables the decoder, and cell, which is goes to the decoder, and memory device, which goes for the memory chips. Here we have a diagram. Normally the 8088 has EPROM located from F800 to FFFFF, which is up to 32 kilobytes. Since a hardware reset starts from execution at FFFF0H, noted that Slower versions of many 2764 EPROMs have memory access time of 450 nanoseconds, and 8088 allows 460 ns. Now, the decoder delays 138, which is 12 nanoseconds, must have use a ready signal to insert the wait state using 8284A clock generator. Now the memory interfacing we have discussed about banks. Now 8086 have 16-bit data buses. Memory is arranged in two 8-bit banks. One is the lower bank, which contains all even addresses, and the higher bank, which contains all the odd addresses. So this is the lower bit one, and this is the higher bank. You can see from this diagram that in the higher section we all have odd numbers, and in the lower section we all have the even numbers. So this is the concept of banks in memory. Now moving to the next, here W1 is stored on an even address. It can be access a single read cycle, and W2 is stored at an odd address, which will require two read cycles. You can have a snap of this page and go through them for your exam preparation. I will also give the link of the slide in the description box. 8086 memory interfacing. Here in BHE and BLE and functions are given below. Here if the both are 00, so both banks are 16-bit. If it is 10, then the higher bank is 8 bits, and if it the 10, then the lower bank of 8 bit. If it is 11, then no bank is enabled. Here are some questions on banks. We have another example where we need to generate 128k into 16-bit. So in the total 8 chips we have 62,256 chips, which can be generated by 32 kilobytes into 8 bits. The 32 is generated by 2 to the power 5, and then here 32 is generated by 2 to the power 5, and then 2 to the power 10 generates the 1k section. So 15 address lines, totally 5 into 10, 15 address lines are needed here. The starting address is 40000, and then the size is obviously 256k, means 2 to the power 8 into 2 to the power 10. The 2 to the power 10 generates the k section, and 2 to the power 8 generates the 256 section. So in the address range will be started from 400, and it will go upon 4000 plus 4000 minus 1, which is 7 FFFF. Then we will get the diagram which looks like this, where the starting address is 40000. Here we have generated 4 here, and all other components are 0. But in the range of high section we have 7, then FFFF, which can be generated by 7 from here, and then F, 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 and F. Here the address lines, the SS and DD. Here D denotes the decode with memory and input output select memory. S is to 2 to 4 decoder, and B is for lower banks. The 16-bit memory interfacing looks like this. Here we have the higher bank, the lower bank, the right section. This diagram will looks like this. This is to design a memory, be sure conduct that into her bus where we have the read and write sections. In this section of 32-bit wide memory, we have 4 banks from bank 0 to bank 3 because each bank have 8 bit capability. So for 32 we need 8 times 4, so we have 4 banks which contains from 0 to bank 3. The figure of those are given below: 0, 1, 2, 3, then 4, 5, 6, 7, and so on. Now we are for 16-bit wide memory, where we have 16-bit and we need to generate 8 times 8 for 16-bit wide memory, and we started from 0, 1, 2, 3, then 4, 5, 6, and 7, then so on till the FF, 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 F. So that's for now. Here the 64 and 32 bits memory division are very much important for our question view. So you need to memorize or practice this section and diagrams those are very easily, and those are very important for your questions. Okay, thank you.